Okay, so this is about the Kaggle Liverpool supported ion switching competition. I'm Jim Davis. I'll be giving the introductory part. My partner, Rakesh Tiwari, he'll be talking about some specifics about the neural networks that he worked on that were a key part of it. I gotta say, honestly, I'm a little intimidated. I hope this isn't pedantic talking to experienced data scientists. A lot of this is going to be kind of introductory level. There's not a ton of technical details, but I hope everybody gets something out of it. A lot of the most important things specific to Kaggle are very simple things that it's easy to forget about. I wanted to thank Richard BJ, the organizer from Liverpool, the Kaggle admins that set it up. They did a great job. Christy Oat, that's just a fellow that we used as public notebooks, and there were a lot of other public notebooks that were important in our solution. One of the great things about Kaggle is that people openly share tons of information. You can get an introductory kernel, just a short program to make some base predictions, get started in the competition and start modifying code. We all know that what you're really doing when you're writing code is modifying somebody else's code most of the time, and Kaggle's great for that. And again, it's been said, but jump in anytime with questions. Actually, I can't see the chat window while I'm presenting, so just interrupt me. It always feels like you're interrupting when we're talking remotely like this, but go ahead. It's nice that I have actual people listening instead of just recording this blankly as I usually do. So this is loosely divided into, is my pointer on the screen? Anybody?
Yeah, we can see your pointer.
Okay. So it's loosely divided into some background, mostly specific to Kaggle. So learning data science by doing Kaggle competitions, I think that's a great way to approach it. Learn by doing, just jump right in. Be careful about how you jump in. I'll get to that in a second. And then the specifics, there was a lot of techniques that we used beyond even just different models that we combined. But I'll talk about the specifics of that competition. Some people might be interested in the some of the details. Rakesh will have more to say about the neural network that he wrote. And then just kind of some conclusions. What it means, what we learned. So all of this is just from my perspective. I don't consider myself an expert in data science in general, but these were useful observations and things that we probably wish that we would have done differently if we had redone the competition, a lot of them. So this is me. The most recent picture is probably 10 years old. By training, I'm a physicist. I went to Ohio State. Right now I teach and do math on occasion. This is a number, actually. We were talking about COVID a long time before the presentation started. This number is a solution to one of John Conway's problems that I found, and unfortunately he died of COVID only a few weeks ago, so it was a large blow to the mathematics community as a whole. But that's about all the math that I've really done professionally, because there was a prize on that also. I'm actually most qualified to give a talk about how to earn money at poker, because until we got quarantined, that's the main way that I supported myself. And earning money at poker is not the same as being good at poker. I would never say that I'm good at poker, and that's related to Kaggle in some sense. I won't try to push the analogy too far, though. This was a placeholder slide. Rakesh, you should have updated it. So Rakesh was an actual physicist. He worked in Basel, I think, for the last decade. He most often gives talks on quantum computing. This is his first Kaggle competition, or maybe second. He actually prepared himself for this one by doing a natural language processing competition. And what that amounts to is learning how to use pandas, because that's one of the main packages that people use on Kaggle. So a strong familiarity with pandas and Python. Some people use R. We focused on pandas and Python. So we were about at the same level in coding ability when we started. This is his publication list. So Rakesh is a physicist, and we've known each other for a long time, which was very important to work together. So how Kaggle relates to data science. There's some differences between a Kaggle competition and I'm sure what you get paid to do in data science. There's important differences. This is kind of a lame way to start a presentation with the Wikipedia definition, but I honestly didn't know what Wikipedia would have to say about what data science actually is, and maybe I didn't know. So it's an interdisciplinary field, obviously, but important is that it uses scientific methods, and then some buzzwords here, scientific methods to extract knowledge from data. What scientific method means to us as scientists is that you're doing experiments to tell you something that you didn't know beforehand about the data. This is what we actually spend most of our time doing on Kaggle. So LGBM, if anybody hasn't heard of that, that's kind of the de facto standard for tree models. It's light gradient boosted model. It was put up by Microsoft. So this is very, very common in Kaggle competitions, writing various neural nets, plotting tons of things about data, looking at the importance of various features that you create and feature engineering. So I think these could all be considered doing data science if you're actually doing experiments that extract some knowledge that you didn't previously have about the data. So to push a poker analogy, at every low stakes and even high stakes poker table that I've sat at, then it inevitably happens that somebody makes a bet and then they get raised by one of their competitors, and then they do what we call in the lingo is they tank, meaning that they sit there, they don't know what to do being faced with a raise, and they think about it for 40 seconds. It slows the game down. It's a little annoying, but more importantly, if you make a bet at a poker table, there's only three things that can happen. Your opponent can call, in which case you have no decision to make. Your opponent can fold, in which case you've won and there's no decision to make, or your opponent can raise. So there's only three possible outcomes. And if you haven't thought about each of those outcomes, you only have to think about one. If you haven't considered that, then you really haven't considered anything. So we do a lot of experiments, even in a Kaggle competition, which amounts to doing an LGB run or starting up a GPU, running it for 10 hours. And beforehand, it's important to ask yourself, what are the results going to actually tell me? Is it going to tell me something more about the data that I didn't know, or am I going to take it in a different direction based on the results? In the last competition, something that happened, I was generating synthetic data to augment training. So you're given training data in a Kaggle competition. You're supposed to build a model based on that. Of course, that has the ground truth in it. And then you make predictions on the test set. If you can find some way to make additional training data, then generally speaking, your model is potentially better. So we generated synthetic data. It took a long time. I think I was going for about 10 million additional points. At one point, we had about 1 million additional points. And I told Rakesh, hey, let's run this, start up the GPU. We'll burn 10 hours of our free Kaggle time and see what happens. And it was nice that he asked me the question that I had brought up before. Well, what are the results of this going to be? If 1 million additional data points does not give an improvement, then we're just going to run the full 10 million, do that augmentation, and see if that helps, because maybe 10 million helps, but the 1 million wasn't enough. If the 1 million data points, if that does help, then we're definitely going to run the full 10 million, do that augmentation. So that kind of experiment, it would have wasted a lot of our time, or it would have wasted money if we're running on Google Cloud or something, but we would have learned nothing about the data, and the next step would have been exactly the same in each case. We did another competition recently, the Alaska 2, and this question came up multiple times. It's something really easy to forget if you don't explicitly think about what the results are going to tell you. All right, so I'll stop with the poker analogies. I imagine some people in here play poker, maybe for money.
We have, there's a member who is actually a professional poker player for 8 years. He's not here tonight with us, unfortunately. You guys would have a lot to talk about.
It's actually surprising. I think there's a few people that have come that have been professional poker players, and it's amazing how much these fields overlap. I think there's got to be something to it.
Well, physics and poker playing, these are the two most common backgrounds for people that come to this meetup.
It's the only things worth doing.
Yeah.
Does anybody want to take a guess at what I'm going to say? Now, people have different opinions, so I'm not pretending to be the expert, but I won't push the question.
I'll guess that it's knowing your competition.
That's not a bad one. What I had in mind, so
is it being able to I don't know, remember what cards have been, like probability and remembering what cards have been played and what's likely to be played?
I get that at the table a lot, because if it comes up that I have somewhat of a math background, people ask if that helps, predicting probabilities. The answer is no. The probabilities, at least at Texas Hold'em, they're trivial to compute. This is what I've got for my students before, bluffing, or I don't know, from just watching TV, all these things. And some of these are really important. Making hard decisions. So this is the opposite of what you want to be doing in a poker game, is you want to avoid hard decisions. But I think the most important skill is table selection. So you can literally be the 10th worst poker player in the entire world, and if you happen to be sitting at a table with 9 people worse than you, then you can win that game. But that might not be why you're there. So people aren't all there just to grind out a few dollars, of course. If you're there to be a better player, then you should probably be playing against better people, like any game of skill. And most people want to have fun, so play with fun people. This is why my partner was Rakesh, and we've known each other for 10 years. This was probably the most fun that I've had that was legal that I can remember, this entire competition. So why are you there if you want to do a Kaggle competition? These are some actual skills. The first one in playing poker is table selection. So decide why you're there and pick the right place to sit. I left out position selection, but we won't worry about that. Hand selection. So I kind of equate this to running the right experiments, and avoid hard decisions. Is important in poker. Set it up beforehand so that you're not making those tough calls. One of my friends actually just was complaining about watching professional pool players, and he said, all they ever make are easy shots. There's a reason that they're only making easy shots, right? Because they set it up so that the shots are easy. So related to Kaggle, not all competitions are appropriate to everybody. We were just in Alaska too, and I think we did very well given what we had. We only spent about $500 on GPU resources because we don't have them dedicated, but we just couldn't run the models that were successful there. So if you want to do image analysis, then just set your goals where they should be there. If you can't run a model that's going to require 500 hours, then you just can't do it. And also, if you're not interested in the competition, if you can't really dedicate the time for whatever reason, or if you just don't want to, then you're probably going to learn more if you find something that you're really interested in. The experiments, again, consider what you're actually going to learn from doing a run. If you're just hypertuning parameters, maybe you hypertune too many. If you're making multiple modifications to a model, then what do you learn at the end of it? It's so easy to spend 3 days with parameter tuning, and then at the end, you're left exactly where you were before. Maybe your model's improved 0.1%, but it doesn't take you in a different direction. Any comments as I move on? I think so. The next one, I'm sure everybody already knows this, but Kaggle isn't a job, although I should mention it can definitely help you get a job. Rakesh, if you want to chime in, I know you've gotten lots of callbacks once you put your Kaggle position on your resume. So it's a good vector to build up your resume. Even just a few competitions, you can speak more intelligently about the common jargon, but you're not going to make a lot of money off of it. So best fitting, he's #1 in Kaggle, I think still, maybe different after Alaska, but he's been #1 in Kaggle for a long time. He might make a lot of money. I don't know. Probably not as much as he makes at his day job, but I don't know the guy. So what we made, we were spending at least 80 hours a week. This is a conservative estimate. The stars really aligned in that, COVID started. Rakesh was taking some time off from his academic stuff, and we had 2 months. We had 2 months free, and we wanted to be working on this for 80 hours a week. But the payout comes. I mean, I don't know what minimum wage is where everybody is, but this is around minimum wage, maybe less where I live. And I'm not complaining at all about that. We were very lucky to have won. It was a lot of work, but a lot of luck. But the real goal is to learn something and hopefully have fun. Because if you're not having fun, then at least I can't actually stick to a project if it's painful to do. So picking the right partner, I think, is important if you want to work with a partner. But with all the time we spent, I can't go into details about everything that we did. That's probably not helpful to a lot of people. So I'm going to try to stick to a broad overview and just look at the models and how they combined. And that's an important point. Somebody mentioned that when I posted a rundown of our solution, which is you have to be able to try a lot of stuff. You hope that some of it sticks, but as you get smarter, you're going to know what to throw at the wall. Most of it's not going to work. I told Rakesh at the beginning, it's a first order approximation. Nothing you do ever works in these competitions. I had done a couple before then. Actually, a lot of those stuff we did in this one worked, so I was wrong about that. But a good competition is one where you can test a lot of different things quickly. If you have to wait a week to get the results of something that's probably not going to work, then that's not a lot of fun on any level. Okay, so moving on to the details about this competition. The biology is, and if anybody wants to jump in and clarify this, we're not biologists. But I think it's important to know the background, the domain knowledge, because that can inform your decisions just as a data scientist. So cells have ion channels on their surface, of course. This is one of the main ways that they communicate with the outside world. When one of these ion channels is in the open state, and there can be multiple open states that are all open, and they all behave the same way as far as allowing current to flow. So when it's in one of its open states, they allow current to flow, current ions, of course. There was a device that I think won a Nobel Prize in the 90s called a patch clamp amplifier. And that's used to just measure current. So what we get is just an amount of current from a patch clamp. And that is directly related to how many of the ions are open or closed in a cell or in multiple cells. In this competition, then there was a maximum of 10 ion channels, and they could potentially all be open or all be closed. The data sets were split, so sometimes an experimental run would only have, say, a maximum of 3 ion channels that could be open or closed. And you can directly infer how many of the ion channels are open from how much current you're measuring in this patch clamp. It has a lot of applications. I think it was mentioned in the competition that it's useful for cancer research, but it's really basic research, so it applies to any time a cell is involved, which is anything that's alive. Yes, eukaryotes. So there's a broad research application. So it's kind of fundamental science, which is nice to work on. I love market research competitions also, but it's kind of cool to do something that's a little bit more applicable to pure science. So here's the problem. What we're trying to predict: you're given a current versus time signal from the patch clamp, and you want to, for every point in that signal, you want to predict how many ion channels are open. So this is what we're given. The axes here, we've got time on the x-axis. This is the current signal. So this would be, test or train data, current versus time. And for the train data, of course, you have the ground truth. So it tells you how many channels are open at each point in time. And then for the test data, you want to predict that. And you see there's a pretty close one-to-one correspondence here. And what we found through some initial EDA exploratory data analysis is that it's pretty much a linear scaling. So it looks like on this little example data, 1.5 picoamps, that corresponds to one open channel. In that case, 3 picoamps, that would correspond to 2 open channels, et cetera, et cetera. So it was basically linear with some deviations in there.
So sorry, just to clarify, so the prediction and the test set, they'll give you the raw signal, which will be on the top, and then the bottom is what you're going to be submitting. So you're giving back another time series of zeros and ones?
Exactly. This set looks like it's zeros and ones, but it could actually be, the signal could be higher sometimes. So one column of the CVS file that you actually submit would be the time in one column, and then the other column would be for each point in time how many channels you predict are open.
It looks like there's a pretty high time resolution here, and so your prediction has to be at that kind of resolution that we're seeing.
Right. So the time points were divided into equal increments, and I wanted to add what those were, but it was going to take me some time to go through my old files and remember it. From the data science point of view, it doesn't really matter what the time interval is, probably. I think it was, I want to say 0.01 seconds. Do you remember, Rakesh, if you're on? In any case, it's a fixed time interval. So you've got...
Yeah, it was 100th of a second. Yeah.
Okay.
Earlier, you said it's very important to pick competitions that you care about and are interested in. I'm just curious, what drew both of you to this competition?
That's an interesting story. So we wanted to work on something together because we had time. I did not like this competition because, in the next slide, I'll explain that this data is generated, at least the ground truth is generated by a Markov model. So I was kind of convinced for a long time that there wasn't much to be done with it, that maybe it wasn't appropriate to machine learning and that the scores were going to max out. How did you convince me to work on it? I think Rakesh got a bronze medal. And so I figured, maybe we should.
So I tried a bunch of things, and they seem to be working. And then basically, I would say this was still early on in the competition. So if you consider in physics, we always bring up the onion. You take a peel off onion, and there are more layers of onions to peel off. So at that point, it seemed like it was not interesting. And as Jim mentioned that, it's a linear thing, and how much improvement there is noise that you simply cannot get rid of. How much improvement can you really have? But I tried a bunch of things. They seemed to work. And then once we took few peels of onions off, it seemed to get more and more interesting. And after that, we hit the point of no return. We just found it too interesting, and we were thinking about it all the time.
The competitions are much more interesting if you can do well. But you mentioned the noise. So there's a lot of noise on top of this signal. And that turns out to be one of the main challenges of the competition.
Can I ask a very kind of a basic question? But if the ground truth is this Markov model, what was the motivation for the competition sponsors behind wanting to do this? So they wanted to emulate their own model with with a machine learning model, that seems slightly odd to me.
I can, Jim.
Sure, go ahead.
Yeah. So from the just point of view of research, getting that much amount of labeled data is simply, it's too demanding. So a human being has to label all the data, and then you can use that data to organize a competition. So in a way, you have to take it with a grain of salt. Like, this is a way of replicating the real situation without investing millions of human hours. So they sort of simulated the real data. And so they already knew the ground truth, which was used only for training. Yeah.
And they're not, so they weren't necessarily, and that I should say that is the traditional method of getting ground truth, is that a person looks at the data and decides what the ground truth is. But why do we trust a person, for one? And they weren't necessarily interested in testing the Markov model. That's taken as just the way that ion channels work. They're interested in, given once what we can actually measure is noisy data, and can we somehow strip that noise out to get it a ground truth. I might answer that question a little bit better as we move on, but bring it back up if that's still unsatisfactory.
Yeah, thanks.
Okay, so right, this is the actually hidden Markov model, I should say. The discussions early on, people I don't think, I didn't appreciate that it was a hidden Markov model rather than just a simple Markov chain. But the motivation for this is that even though these ion channels are fundamental, of course, we can't do a full quantum calculation to simulate all of them. And I'm not a molecular biologist, but I doubt that people understand exactly what's switching them on and off at that level of detail. So this is what they were doing, as we mentioned. People look at the current versus time plot and they guess which channels are open. But the noise spectrum can really, the noise can be greater than the baseline signal. So even a human looking at it might make mistakes. And in reality, if you're looking at real data, you don't know how many channels are open. All you have is the signal. So you're relying on somebody to guess what the ground truth is. There's no ground truth with just purely real data. So you do this hidden Markov model simulation, and evidently the biologists have good evidence that this is how they're behaving. So it's called simulation, synthetic data, whatever you want to call it. The standard is this HMM, the hidden Markov model. The Markov model, of course, just means that it only has one step of memory. The next state only depends on the current state of the system. And the fact that it's hidden, I'll go into the actual graph of what that means in a second. The hidden part, so I should mention, it means that you can't observe the actual state of the system. Just some output signal is measured, but that output signal, in our case, that's the current. That doesn't actually tell you the state of the system. The state is more complicated, so many states might be giving the same output signal, and we don't have a direct way of measuring this hidden state.
Hey, Jim, the bottom of your slide is cut off a little bit for me. I can't read the line beneath hidden Markov. I don't think it's affected anything so far, but I'm worried about maybe some of your later slides. Is it just me?
It's not just you.
Yeah, same for me.
Sorry about that. I'll make sure to let me know if it happens, and I'll read it. So the rest of the text is the state of the system isn't directly observed. Only some output signal is measured. And as I mentioned, in our case, that's the current from the patch clamp.
I think it's a good metaphor for a hidden Markov model. The state of the slide is not directly observed. It's somewhat hidden.
Very good. Okay, so this is the important hidden Markov model that they made for the data that was hard to predict. So there were two of them. I think the next one's in the next slide. The metric I don't go into detail about. It was an F1 macro averaged metric, but what it amounted to is that the high occupancy states, when we have 10 channels open or 9 channels open, that's what really hurts the score. The lower number of open channels were easy to predict. We were quickly getting 99%. So this model that had potentially high numbers of open channels, that's where the improvements were to be made. So in this graph, the Ks that I'm sure you can barely read, but there's little subscripted Ks on each one of these arrows. These are called transition rates. So go ahead and imagine that if we have, in this model, if it's a max 10 channel model, then there'd be 10 black dots floating around in some of these ovals. And then the dots, which are the states of which are the ion channels themselves, they move back and forth between the ovals at a rate that's given by these Ks. So they'd have units of inverse time. If I have one channel in this closed state, then every 10 seconds it transfers to the open state of 2, if that's the transition rate. So they're moving back and forth stochastically. There's several closed states and there's several open states. Each open state produces the same amount of current. So there's lots of degeneracy here. If we have a certain amount of current, then we can possibly predict how many channels we have in the open state, but we don't know exactly where they are just from that current reading. Again, that's what makes it a hidden state. And the actual signal is based on how many of the ions live on the left-hand side. Is there a question? Okay, so I should mention this was GitHub code from their project where they actually stored the simulation that they did to create the train data and the test data, but it was not the easiest thing in the world to find. So I think some teams didn't find this until toward the end of the competition. It was also in the original paper. So a little more background is that Richard's team made a neural network to do exactly what the competition was about, and that was published beforehand. And then the competition is kind of, can anybody make a better model?
Maybe we can go back to the last slide. I'm reading the point oval states read as open, more open, really open. So you're talking about the states on the red states. Does this imply that you can't go from like a more open state, which I guess would be 5? You can't go from that to closed. You had to first go through 2. I'm not quite sure I get this.
So that's a more complicated question than it sounds.
Sorry, yeah, you don't.
No. So you can't directly go. You can only go between the connections. Okay, so the physical reality that we're trying to model here, we can only transition from 5 to 6 or from 5 to 2 if that's the state that the ion channel is open, that it starts at. That's not entirely the case. So when I started doing simulation, because those time divisions are discrete.
Oh, right.
It's possible that within one timestamp to another timestamp that it's done something amazingly improbable, which is very probable when you have 10 million data points, that it's gone from 2 and then to 1, between the time that you've measured. So all these transitions are possible when you make the time discrete, but in reality, no, they're only connected the way that it's shown. Okay, so we also had the low occupancy model. This was for some of the data. And if you go into the GitHub code, this MATLAB code that they use to make the data, this model actually has 25 ion channels living in it. It's called low occupancy though, because the rates from going going into the open state are very low, and the rates going out of the open states are very, very high. These models started out in closed states, so if you run them for long enough, then you'll start to get more than one ion channel in an open state, which is relevant later on, not so much for the score, but interesting. The maximum is actually 25, although that never happens in this channel. It's generally between 0 and 1, and this model was very easy to predict. It was most of the private test data, though, was within this model. Oh, and the rates were all from actual measurements. So these are fairly realistic models of what the channels are doing in real life. Okay, so our first EDA, I'm going to go through quite a bit of EDA. First, this was explained in the competition also, but the test data and the train data, they're divided into chunks, which correspond to like experimental runs. We're going to turn the patch clamp on for 10 seconds and collect data there, and then put it onto another physical system and collect data for the next 10 seconds, which isn't related to the first. And those systems that we're measuring or really simulating, those correspond to having a total number of ion channels between 1 and 10 max. The second part is that when you actually run through the paper, the data isn't entirely synthetic. The model's synthetic, so the ground truth is synthetic, but what they actually did was they simulated the patch clamp itself, and then they piped it through the actual machine, so the wires, everything that's connected to, so that the noise that you're adding on is real world noise that you would see. So these experimental runs that had low number of maximum channels, those were easy to predict. You can kind of just throw that into a naive LGBM model and be done with it. But when you get into the higher number of channels, that's where the score would take a hit because of the metric of the competition. The metric's important. I just probably don't have time to explain it. And finally, the hidden Markov model, if you know the state, which you don't from just the signal, but the current state of this hidden Markov model is everything to know about the system. It doesn't have any memory behind it. So the simulation code's public, so theoretically you can make your own data and increase the training set. The code, this might be cut off though. The simulation code, it was linked to, but it wasn't exactly easy to find, and it's in MATLAB. So just as a public service announcement, if anybody has to use MATLAB, I'm sorry, but NumPy is kind of hopefully taken over because not everybody has licenses to MATLAB these days, and NumPy is just getting better. 10, 15 years ago, matplotlib didn't exist. Okay, so we had a lot of approaches here. First, LGBM, feature engineering. This is just creating new features out of the data that you're given, and see if it improves the score. You can also check if LGBM thinks that that feature is important. Then you can make a feature importance plot and keep the ones that are really good and ignore the ones that aren't. Centered rolling windows. So since this is a hidden Markov model, I said that the current state is predicted entirely by the previous state. It's stochastic, but all there is to know about the transitions can come from the state before. But it could also come from the states in front of it. So you can do a time reversal. Of course, the rates reverse, but it's not really time series data because there's as much dependence on the forward data as there is from the previous data. So time series is not an appropriate label for for this simulation. So you can make centered rolling windows, meaning that we're taking averages and putting that into as a feature for prediction for a certain data point, but that looks at data ahead as well as data behind it. Memory reduction, this is just a technical point. Keep in mind what you're dealing with. If you've got a bunch of floats, sometimes there's long ints that you might not look at. You don't need that level of precision probably. So you can do a lot more if you change your long ints into something smaller. The features that we use, some of them, power. So coming from a background in physics, that's just signal squared or proportional to signal squared. That was a really helpful feature. Also, signal squared minus signal mean was helpful. Derivatives, secondary predictions. I could talk more about this. What we actually did at the beginning is instead of predicting the ground truth, you can just tell your tree model to predict the amount of noise. And you can calculate that as just ground truth signal minus the actual signal, and do that as a secondary prediction. That actually blended fairly well. It wasn't as good as the later things that we did, but that was helpful in initially boosting the scores. Analytic models. So Bayesian updating, Bayesian inference. I spent weeks writing these models. In the end, they performed almost as well as machine learning, but we didn't end up using them. So I'd like to explain all that, but since we didn't use it, it probably wasn't as helpful as I had hoped. Data augmentation for Monte Carlo. I wrote my own Monte Carlo, and I'll explain why, to simulate the data. The code was also available, but it wasn't working for us. Another idea was unhide this Markov model. So if you can write your own model, instead of just outputting a signal, you could output the actual state. So where each of the ion channels were in those diagrams. And that's additional information to pipe into LGBM, so that presumably it would make a better prediction. Cube, this is standard software for ion channels in particular. So it can do two things primarily. You can give it a model, you can give it a hidden Markov model, and it will simulate the data. It'll give you a signal out. You can also give it a signal, and it will try to predict the model or the transition rates for the model. This was helpful, but not as much as we had hoped. And then finally, noise reduction. I think this is what the competition was really about. Fourier transform, that was a lot of teams' approaches. So just take it into frequency space, see if there are any spikes, and take out those spikes. The problem with doing that purely in Fourier space is that a fast Fourier transform or a discrete Fourier transform, it's going to give you data in real space. So you're kind of losing the phase information, and replacing unwanted frequencies, you have to replace it with something. And you can't really intelligently decide what to predict those noise frequencies with. So what we ended up doing was a single frequency removal in real space. All of these machines that they pipe the data through, they're connected to outlets. And in Europe, that's a 50 hertz signal that is difficult to get rid of if you're not really trying to get rid of it. There was 50 hertz noise that was really messing up predictions. And this can also be automated. I think that's more of a science point if you want to do this fast. And then finally, Wavenet. This is probably cut off. But
yes,
Wavenet,
so we can't see the bullets underneath Wavenet, so talk us through it.
So this is just, what did I write here? No, I can't see it. So Wavenet's actually designed for signals. Rakesh is going to talk about this. But this was interesting in the competition in that somebody posted a Wavenet kernel. Other people have been using neural nets to no success. When the Wavenet kernel was posted publicly in the notebook section of Kaggle, then the leaderboard changed entirely. So everybody's scores improved. Everybody was using Wavenet at that point. So watch the discussion is the point, and really read everything that comes on the discussion. that's also where you learn the most. Okay, so a lot of this is exploratory data analysis. So first in feature engineering, one, I don't know if this counts as EDA, but read the background literature. A lot of people win these competitions from knowledge of the field, or at least it helps. We didn't know anything about HHMs, but a few days of studying, and it's not unapproachable. So for one, it's not a time series. We figured that out. An HHM doesn't make a time series, at least not in the sense of a normal time series, where you can't do certain things. In other words, a centered window for our features would have not been appropriate for proper time series data. At least that's my understanding. Each data chunk, so each physical run, it turns out they start in the same initial state. So you wouldn't know that unless you're making kind of crazy plots just looking at these signals and hundreds of them. And every so often they just jump up into a completely on state. But it seems like that's what was happening with every run. That helps your model mostly because you know what data to put in there. You can divide your training data into these sections because the test data is going to be divided that way. And that's hard to see if you're not just spending all night making plots. The simulated data, so this software called Cube, that can give an idea if we just simulate more data and vary the parameters, see how much sort of memory the system has. To put it another way, how long does it take for the states to transition out of that initial completely on state into some lower states? So maybe I shouldn't use the word memory, but that gives an idea of the time scale of the system or the relaxation time of the system. So any feature that's looking beyond about 100 time steps, it doesn't matter because the system's completely randomized at that point. The time lengths of runs, these were actually varied. They were not all 10 seconds, although that was the assumption that we were running on, and I think almost everybody was. The maximum number of open channels was also different. So that low occupancy model actually could go up to 25. It didn't, but because the time length of runs varied, then it went up to about 4 in the longer runs. Again, not a big deal with the actual score, but it could have been. And then probably finally cut off at the bottom. I'm asking, are the transition rates accurate? So from the paper, when I duplicated the model in Cube, I got different numbers, which is what motivated me to write my own simulation. This is going to be a little bit of a side shot, but I think there's some valuable tips in here. And this is something that happened kind of at the end. Rakesh will talk more about putting features that are too good into a model. So if you've ever used LGBM, then you're going to see on the right here, you're not meant to be able to read this, but these are feature importances, and it makes a little bar graph for you. And this is one of the only forms of feedback that you get from LGBM. But keep in mind, if your model is not perfect, then it doesn't actually know how important these features are. One point to keep in mind looking at these plots is that if multiple features are correlated, then each one is going to be ranked lower importance. So this is from a competition a couple years ago, but three of these are ranked lower just because they're close to the same feature. And if you do an average with those, then it swamps out all of the other features, even though you can't tell that on this plot because you've broken up what's effectively one feature into 3. Also, a big problem, random data, it can give a rank of importance or a positive gain on data that's effectively random. You can fix this by taking a feature that you think might not be important, shuffle all the labels around. So just randomly reassign true and false, pipe it back into there, and if it still thinks that the feature is important, then it was never to begin with. there's techniques explained on Kaggle. That's where I got all these ideas. Just start removing low importance features until you see a score hit. You can remove highly correlated features because you probably don't need both of them. Just do a pandas.core and see what the Spearman correlation is between two things. Always trust your CV. And the last one is you can also just split your features and make two models. That usually doesn't work, but very occasionally it does. And then do a secondary blend. How am I on time, Matt?
Well, we would have 20 minutes left if we kind of add an hour, but if Rakesh needs to kind of spend a little bit more time, I think that we're happy to go over a little bit to get the full explanation. So,
okay, I'll speed it up a little bit here.
Yeah, it'd be nice not to leave Rakesh like 2 minutes.
Yeah, sorry, Rakesh. Okay, so the secondary EDA was with my data augmentation, or what I'm just grouping into analytics. By that I mean Monte Carlo also. So the Cube software, I said it did two things. It can just simulate a model, and it does that fine. But the simulation with the parameters didn't match the training data. You can see that by visual inspection, and I wrote a bespoke autocorrelation so that I could actually get autocorrelations. That didn't match, so I wrote my own model to make additional data. It also claims, so this is a side note, but I think Cube is becoming abandonware. It claims to be able to reconstruct transition rates with enough of that time series data, which would be the actual competition data. But if you think about those models, those are 10 coupled differential equations, and it can't do that. Nothing can solve these 10 coupled differential equations with millions of data points and get reasonable results in a few hours. So that never worked out. So to mimic the competition data, my simulation had to have noise in it. And the easiest way to pull noise is to understand the noise, look at what the noise spectrum is. So here's the 50 hertz noise removal. This was spoken about in the discussion that there should be 50 hertz noise, and people did see plots similar to this. This one's mine. This is actually what you're seeing is signal again versus time, but this is after I've removed our initial predictions. So how much signal should be due to the actual ion channels, and what's left over here is just noise. And this doesn't look like a fantastic fit to me. You could probably convince yourself that there's something sinusoidal going on in there, but I don't know that I trust that conclusion. So one of the key ways that we made improvements was a couple of observations. One, the 50 hertz signal, it's not perfectly 50 hertz. So there's drift out of any outlet. If you just try to slap a 50 hertz sine wave onto here, eventually it's going to go out of phase. The Fourier transform I mentioned might not be the best way to do this because you're not necessarily capturing the phase correctly, and it's definitely not going to capture the drift perfectly. And if the experiment resets at some point, then the phase is going to change. The solution we came up with is that, again, we subtract off the initial predictions so that this noise signal and the 50 hertz wall noise signal is bigger, and the remaining noise signal, label it, in our units it's modulus 200, but it's so that we get the same label at the same phase of the cycle of 50 hertz. Then you can average those cycles, that smooths it out, then plot it. So you smooth out some of that extra noise and you come up with something that looks much more sinusoidal. So this is subtracting off initial predictions, averaging a few periods. So this is noise, and it's a pretty clear signal of the 50 hertz noise. There's some cutoffs here, and that's from the way that I plotted it, but that indicates a little bit amount of drift through the run. So it's changed maybe from 50 hertz to 50.01 hertz. Okay, so further EDA. There's some places that this failed. So if it was completely automated, you wouldn't notice this. This really can't be fit appropriately because there was some strange drift in the middle. So the fit failed. And it's good to actually be able to look at that, and so you can trust what your automation is doing. Then at the bottom, this is to get to one of the key discoveries is on the bottom. Does anybody have an idea what's going on here? I just taught this in class actually, and I brought up our competition, but it looks like the amplitude's increasing. I had assumed somebody just stepped on the wire or something at this point. This was the most important set of test data that was hurting our score. And I'll explain what is actually going on here in a minute. And I want to get to Rakesh, but just to quickly recap, we did LGBM models. I'm making simulated data. That's helping. The LGBM actually got us to bronze. The simulated data augmentation got us to silver. And then we started to look test versus train. There were also some deviations in that. So we picked the right test signals that matched the correct test data to match the correct train data to match the test data, because there was some variation in there. Okay, so Rakesh,
Jim, can you pull up that last window? We can't see that that histogram there.
I think I'm probably just gonna shift. I'm probably just gonna skip it.
Okay.
So that Rakesh can talk about Wavenet. The key point is just that some of the train data was more closely matched to the test data, and yeah, an adversarial network might have been useful for doing that, but this was not. This didn't require it. Are you ready, Rakesh?
Yep. So any questions for Jim? All right. So I'm going to talk a bit about Wavenet, which was a useful model for this competition. So I am going to share my screen. Okay, so now that Jim has stopped, let me share. Let me know if you can see the screen. All right, can you see the screen? Okay, so one thing I wanted to clear is about that question about the timestamp. So I read it. It's actually 10 to the power minus 4. 1, 2, 3. Yeah, 10 to the power minus 4, not 10 to the power minus 2 seconds. So the resolution is really 10 to the power minus 4 seconds. All right. So with that clarified, let me start with Wavenet. All right. So what is Wavenet? Well, it's a deep generative model based on deep neural network of raw audio waveforms. And it's a model that was developed by the DeepMind team at Google. And in the bottom, you can see the reference of the paper. It's a model they published in 2016. And it's a pretty good model. So these wavenets, they are able to generate speech that can mimic any human voice. And it's there are some modifications on it, but it's one of the best neural nets that's out there. So text-to-speech systems, Wavenet is the way to go, or modified. This is the base model for these kind of tasks. And I'm showing two figures from their paper. The left one is just one of the things that this model generated, and it's just like an audiograph of it. And on the right one is the architecture of Wavenet. Now, you will ask, like, oh, this has nothing to do with ion channels. Yes, it has nothing to do with ion channels. And if you stare at the blue curve, you will see some similarity. Remember the curves that Jim was showing, these current signal for various ions? They were somewhat similar to this blue figure, the blue audio graph. And that's all. Still, like, it's far too, like, I would not have guessed that, oh, Wavenet is the way to go for this system. It's like a text-to-speech system. Just basing it on observing that this blue image is close to the data that Jim showed, one would never guess that Wavenet should work, but it does. So that's a lot of what I learned about this field, that you just have to try the models, and sometimes they just work, and it's tough to explain why it works, but it does. So just take a leap of faith that because this blue graph that Wavenet generates is somewhat similar to the signal that we saw for ion channels, Wavenet might be able to do something reasonable. And it indeed did. One of the main ingredients of the Wavenet model is actually what are called the causal convolutions. What that means essentially is these are convolution neural networks, one-dimensional. You can think of them as one-dimensional. And the way these neural networks work is that they propagate information in a way that causality is preserved. Now, that is important for a time series. What that essentially means is that at time step t, you make a prediction that is not based on knowing the value of the signal about future time steps. Now, as Jim mentioned, in this competition, we did know the future time values also. So we added that information in terms of features in the signal, and we actually used that information. So in short, if there is any information that is available to you, any additional information, absolutely use it. It never hurts. So even though we will use this Wavenet model that has convolution neural networks that preserve causality, we will provide some of the future timestamp signal values as features in it. So on the right is just the typical architecture. There's no point in going through details of it. The paper does a very good job of explaining it. What we need to do is modify it a bit so that it's more suited for our task. And luckily, we didn't have to do anything at all. Well, we had to change things a bit, but there was this wonderful kernel that appeared on Kaggle, and that really changed this entire competition. And that kernel basically encoded the Wavenet model tailored it for this competition. And so we were at that point in the competition, we were using LGBMs, and we were getting scores of around 940. And this public kernel comes and everybody has a score of 944. We were feeling pretty good. And then the next two days, so we were really around bronze medal range, and we were like, oh, this competition, it's fun, we are doing well. 2 days later, we're nowhere, because 200 people used this kernel and they got a score of 944. And so it was around weekend, and then 2 days later, and we were sort of like, what happened? So we obviously, if that happens in you're in a competition and that happens, my personal experience suggests that just jump on the new thing. It might very well be possible. So keep working on the things you were doing a little bit, just to try. Maybe it is still, there's time to improve it. But if there is a drastic improvement that is provided by another method, you should jump on that method, at least learn it, see if you can augment it with whatever you have learned yourself so far. You can use that information to make that model that already works very well even better. So that's what we basically did. We jumped onto this Wavenet, and at that point, it took me I was really surprised why Wavenet works. To be honest, I still don't know the answer why it did so well in this competition, other than just say that it simply did. So the final output layer was modified to have 11 neurons or 11 units because we want to predict whether the number of open channels is 0, 1, 2, or till 10. So there are 11 possibilities. The loss function, it used categorical cross entropy loss, good for classification problems. This is also another thing that whenever a good public kernel appears on Kaggle computations, like you can always modify things and do your own personal experiments to see if there is potential for improvement. It's hard to improve those kernels because typically they're written by experts. Hard to improve those kernels by just minor hypertuning. But because in our case, we were changing a lot of things. So we had to fine tune a little bit every time because we added a lot of augmented data, which came from various sources and so on. So it's good to change a lot of things. That means try different loss functions, try different learning rates, try a bunch of things whenever you make some big change in your model.
Hey, Rakesh, did you try any like regression based loss functions?
So in this, for LGBM, we use that, but for neural nets, it essentially outputs whether, like it's a classification with 11 classes. But for LGBM, essentially it's a regression, and then we round. It's a regression as in you predict on a linear, continuous number between 0 and 10, and then, or well, say -1 to 11, and then you round it. But for neural nets, they're not really well suited for regression in a way. I mean, there are ways to do it, but for classification problem in neural nets, it's better to use these discrete. So 11 classes, yeah, and that's it. So the different features that went in, signal, which is I'm calling S, then the signal square. And here we provided the information about future timestamps. So we provided the neural net, the signal value plus the signal value at 0.0001 seconds, 0.0002 seconds, and 0.0003 seconds. And that actually helped the score a fair bit. And then we also added another feature, which were the LGBM out of fold predictions. And those are predictions made on the training data out of fold using the LGBM that Jim was talking about. So a lot went in calculating those LGBM predictions, and then we used that as a feature for Wavenet. And then caution, and this is what I think a lot, or can't be certain, but I think a lot of our competitors, like they actually got hurt in their final scores because the out of fold predictions that they were feeding in were simply too good. So imagine it in the following way. Say you have, so this model has a lot of parameters. So if the problem is very complicated, all those parameters are going to be very useful. But if along with the original data, you're sort of giving it a feature which is more or less a very good answer to the predictions, then the problem is much simpler. And you're still using a model with so many parameters, it's bound to overfit. So a lot of our competitors, I think they did not realize this, that Wavenet, at least for the parts of the problem where the number of open channels is only 0 and 1, the problem is simply too simple. You don't need a complicated model to predict that. LGBM model is good enough. And so we realized that, and we sort of put that to good use, and we used Wavenet essentially only for the difficult parts of the problem. So resources, I'll just quickly went over. Also, in this particular, I'll summarize very quickly, a few minutes. So the resources, they're sort of very important for a Kaggle competition. This particular competition was useful or easy in a way because entire training was done on Kaggle. Kaggle gives you 30 hours per week and you have a K80 GPU, and that was sufficient for this. The only thing I would say here, because it took me a lot of time to figure this out, so because I just joined Kaggle 6 months ago, so if you are in that situation, maybe one of the main things you can take home from this talk is after you hit commit, turn off your kernel. If you do not turn off, it will cost you time from this 30 hours. So optimize the 30 hours of computational time, the free computational time that you have on Kaggle. Now, for some competitions, this 30-hour per week is not going to be enough. Most image competitions, and we tried, you can have a lot of good ideas and they're very useful, but you need to be able to try them. So for image competitions, you will absolutely need to work on platforms other than Kaggle. So one of that is the Google Cloud platform. And because a lot of you are already working on data science, I'm assuming all this is well known to all of you. Just if there is somebody who does not, if you are a first time user, you get $300 free credit. So you can use that. And starting with running a Jupyter notebook on the Google Cloud platform, it can be a bit hard, especially if you're using GPUs. You have to install these CUDA drivers and so on. And it can be done, but it takes time and it can be frustrating. So there is an easy way. Another good take-home message from the talk, which will be valid for all future competition, is I learned that if you search how to do something on internet, you will find a lot of links and a lot of wonderfully written posts, and you start implementing them, and then you find that that post was written an year ago, and some new versions of some of the softwares that they're talking about exist now, and it no longer works. So one of the easiest things to do is to use this deep learning virtual machine, deep learning VM solution that is available on Google Cloud Platform Marketplace, and it has click to deploy option. So you can just customize the template, the instance template, choose an environment, whether you want to use TensorFlow or PyTorch, and it will create an instance, install all the libraries for you, all the drivers for you, and that saves a lot of time. Also, to start Jupyter Notebook server, it can be hard, and I personally it's not hard in the sense that it can be done with few hours of dedication, but it can be frustrating because things might not work out of the box and you'll have to struggle with them. So I would recommend using the AI platform interface on Google Cloud, and it's very easy way of running Jupyter servers. And so you get automatically installed all drivers using the deep learning VM solution, and you can easily run Jupyter notebooks using the AI platform. And I think this might be a very important lesson, at least for me, after spending so many hours just getting things to work. Yeah. And also computational limitations can be frustrating. So back to table selection, select the competition where you have the ability to try everything you want to try, or some of the things you want to try. And otherwise you will have a lot of ideas. You will not be able to try them. And it can be frustrating, because not just frustrating, it could very well be that some of ideas would have worked. So keep in mind the resources you have. Another thing I would say is Kagglers are extremely smart people. This is something that cannot be understated. Do not underestimate other teams. It doesn't matter how much expertise you have, domain knowledge, still always watch discussions, hear what everybody else is talking about, and you can use a lot of what other people know to make your own models better. And few more things that most probably there is going to be a shakeup at the end of the competition. Develop a good strategy for creating a robust local cross-validation score, which you can rely upon. So this is very important because towards the end, there is a daily submission limit on these competitions, and it can vary in the competition. Sometimes it's 1, 2, sometimes it's 2, 3. In this competition, it was 5. But to be honest, for me, it feels like this is not actually that restrictive. It's can be a blessing in disguise. What I mean by that is towards the end, if you still have a lot of ideas that you want to experiment, you join the competition too late. And so you have to join the competition at right time. So it's simply not enough time to try out all of your ideas. So select which hands you're going to play and just play them well. So in my opinion about this restricting few submissions is that I think it actually helps in trying to think a bit more rather than just brute force, keep trying, whatever works or not, and actually makes your model better. So also know the metric that is used by the competitions to evaluate your score. And if there is any scope, so say you have a model that makes some predictions, sometimes you can process those predictions to some post-processing and get a better score. So keep that in mind. And try to improve model a little bit every day. There will be days it won't improve. Okay, don't get disappointed. Note down the results so you don't have to do the same experiment again. Now, in our case, it took many small improvements for us to climb on to the top 20 on the public leaderboard. They were very tiny increases. Sometimes it will be only like few places and sometimes 10, but there were many small ideas that went in. So there was a lot of work to get the model in the top 20. So small improvements do matter a lot. But if you look at our final score, you'll see our final score was way beyond that anybody actually had, like long shot. So our final score reflects many of these small improvements that we made over the course, and there was a huge jump. And this was due to the leak. There was a leak in the model. We already had a very good model at that stage. And in the last week, we found there was one more thing that we found. And well, that just simply made our model unbeatable. So I think we had like 985 or something. The second team, they also knew the score. They had like 958, still quite low. But everybody else was in 94s. So we had a very high score. Most of it was from small improvements, small jumps. But I think we would have saturated around 9.4 or something. But there was a big jump, and that was something that was due to the leak that was present in this data. And with this, I will hand it back to Jim. And if there are any questions about Wavenet, please ask. It's getting a bit late. I have a very young daughter, so I'm probably going to sign off after this. So if there's any question about Wavenet, I would be happy to answer.
Okay, I'll come back and I'll just really quickly summarize what the leak was and wrap up, okay?
Yeah.
All right, well, because Rakesh might sign off, thank you so much for joining the meetup, Rakesh.
Oh, it was a pleasure.
Really great.
I might join some other talk also, if you don't mind.
That would be great. Actually, like I think there's such a great opportunity here to bring a larger Kaggle community together and all share ideas. And so thank you. Yeah, I mean, I'll thank Jim again later, but if you're signing off, thank you so much.
Yeah, thanks a lot. Bye.
Okay, am I back on?
Yep, we can see you.
Okay. Okay, so just to explain what the leak was, this plot that I left hanging, this amplitude variation is actually a beat frequency. So a beat frequency arises when you're adding, two sine waves that are slightly off in frequency. So if you expanded this further, you'd see the amplitude increases and then it decreases. So physics 101 stuff, very cool. So knowing that this came from two different signals, I looked at, it's a slide, sorry. So I looked at, and also in trying to get training data that more closely matched the test data, I just checked the correlation between all of these different chunks of data. So divide them into the correct chunks and see if any of them are more correlated than others with the test data that we're actually trying to predict. And one of them had a correlation of 60%, which would be absolutely impossible if they were entirely separate data sets. So what it turned out had happened was that this maximum 10-channel set was a combination of two max 5-channel sets. And one of those max 5-channel sets was in the train data. So you could just subtract off that part of the data, and what you're left with is something much easier to predict, which is a max 5-channel set. It was asked in Kaggle. It's a very good question. I don't think I answered, but a leak is, unintended data that wouldn't be available in a real situation. I don't know how to answer how do you actually look for them. What we were doing was just EDA and other things, and there was tons of good EDA in the competition. I'm not going to claim that ours was better than other people's, but it was a hard leak to find, and we got lucky that we were looking at the right thing. Only a couple people out of the competition found it. I'm going to skip the signal histograms. And yeah, this is what I did. I just checked the correlation. It's literally one line of Python code, well, maybe 3 lines if you want to make a loop. And the signal really popped out very clearly. There were prior clues. There was this beat frequency was the main one. And I'll just wrap up then. So the conclusion we came to, and a lot of the top teams also came to, was what this amounted to was a real-world noise cleaning problem. From an experimental science point of view, then I think this might be solvable by using a cleaner power supply, maybe even some shielding. A piece of aluminum foil might have eliminated a lot of that 50 hertz noise. It can be automated efficiently, but you still want to actually look at what you're removing and make those plots, and always check your assumptions about the signal by making the plots and looking at what the signal really looks like instead of just printing out statistics about it. We didn't talk about drift. That was a big part of it. But once one person does it, if it's public, then most people kind of tend to move on to better models. And then finally, again, MATLAB. If you didn't know MATLAB code, if you have MATLAB code that you can't run, there's a program called Octave, and that'll run most, if not all, MATLAB code. So look into Octave. You can run it if you don't have a license, but if you're writing in MATLAB, then just be aware that it's not going to be accessible to a lot of people, and NumPy is quickly catching up. And that's it. Thanks so much for having me, and I'd be happy to talk offline with anybody.
We can take any questions if anybody has any.
Yeah, I have a question about your 50 hertz removal. You said that you didn't just run a filter in Fourier space because of some question about what to replace the removed signal with and a phase shift. So I do physiology experiments, and we regularly run, well, here it's a 60 hertz filter to get rid of that noise. And so like, what's going on? Are we doing it wrong? What's better about your approach compared to that?
So I can't say you're doing it wrong because I really don't know. This was mostly because neither of us trusted what was going to happen with just a straight removal in Fourier space. If there is, in our data, there was potentially a cutoff where a new experiment would start for whatever reason, and so you'd have a dramatic shift in the frequency. In real life, maybe that happens just because the power company has some wiggle in what they're sending you. So if that happens, I don't think that removing it in frequency space is the best thing to do without looking at it. But I'm not an expert. I could be totally wrong about that. We just didn't trust it. I trusted looking at the sine plots and then looking at what we were removing.
Okay, so basically just check the data by eye before and after, like actually.
Right.
Yeah, we do that, of course.
Right.
Yeah, and then in your data, it just sometimes had this funky jump thing, and that's the reason that you couldn't just hit it with a notch filter or something.
Yeah, exactly. If you had to do that on a large scale, then, I mean, you can't sit there by eye, obviously, and look at 10 hours of data every 10 seconds. Sure. So that's not really an option. But for a Kaggle competition, you can. So
yeah, cool. Thank you.
Yeah.
So Rakesh said that he was a bit confused about why Wavenet was so useful in this competition. So as an audio guy, I could take a couple of minutes to give some thoughts on that if there's interest.
Yeah, go for it.
I'd love to know.
Maybe I'll try sharing my screen because Wavenet made a good blog post when it came out. It shows how it works. So yeah, the big problem with audio is there's very high sampling frequencies. So you're taking tens of thousands of samples every second, and then you're interested in things that are happening over multiple seconds. So you have a ton of samples, and that's where audio is pretty similar to this competition, because in this competition, I think the sampling rate was 10 kilohertz.
Right.
So that's up there with audio type sampling. So other things like RNNs and LSTMs and these types of other architectures are pretty good at handling like tens, remembering for tens of samples in the past, or maybe hundreds, but tens of thousands is too much. So the big problem is receptive field, basically, is how wide of a field can your neural network remember things. And the thing that's clever about Wavenet is it has this way of turning the receptive field and making it go exponential in the number of layers rather than linear. So the way they do that is by using dilated convolutions. So each layer is skipping a different number of samples. So the second layer here is skipping 2 samples, and then it's skipping 4, and then it's skipping 8. And so this gives it a really wide receptive field, basically. So it's able to remember information over a very wide number of samples. And it's exponential in the number of layers rather than linear. And that's sort of the clever thing that Wavenet did that makes it good at audio, and presumably is also the clever thing that makes it good in this competition. So does that kind of help it make more sense?
Yeah, that's interesting, because the memory of the system actually was thousands or several thousands of samples. Yeah, so that does make sense.
Awesome. Thanks, Dan. Okay, I'll give it a few more seconds. Okay, so thank you, Jim. This was really great, and thank you for agreeing to present. One thing we like to do here is kind of like give people a round of applause. Better in person, but we'll still try to do it remotely. So on the count of 3, if everybody could just unmute themselves in the next few seconds, do 1, 2, 3.